Today I'd like to talk a little bit about developing applications for heterogeneous devices. I'd like to go through, first of all, some of the advantages of these devices, and then look at some of the development tools and how to develop applications for the different processors on the system. And then we'll finish up by having a look at how to manage the interprocessor communication and creating a bootable system. Again, as you have questions, please raise them as you go along, and we'll come back to you after the seminar. So in about 2006, ARM released their next generation of processors that they called Cortex. The Cortex processor was arranged to have three different profiles that ARM called, first of all, Cortex-A, which was their application processor. So this was designed to go into their core applications, mobile phones, so that it could run feature-rich operating systems like embedded Linux. They also created a profile of the Cortex processor called Cortex-R, which was a real-time processor. So it's a high-performance processor, which we don't really tend to see in standard devices too much. It really is more targeted at deeply embedded applications such as automotive, disk drive controllers, etc. And then probably the most widely used of the Cortex processors is Cortex-M, which was really targeted at small microcontrollers. So again, I suspect that most of you looking today are using Cortex-M for different types of microcontroller applications. So this is very much a real-time processor that took over from ARM 7 and ARM 9 that were previously being used in small microcontrollers. And of course, the names of the profile spell out ARM, so probably big cake in the marketing department that day. So what we are starting to see now is a number of application-specific devices which have typically used the Cortex-A processor to create high-end devices capable of running these sophisticated operating systems. But now manufacturers are starting to incorporate additional processors on there, typically the Cortex-M device. There are some that have Cortex-R on as well. So now we're starting to see these heterogeneous devices which are capable of supporting a Linux application development, but also we have the Cortex-M processor which can run a small real-time operating system and deal with very real-time applications. So these are quite interesting devices that are combining these two very different processors. So the sorts of applications that these allow you to develop for is to have a Cortex-A processor running your Linux operating system with an advanced user interface, high levels of communication over TCP/IP, USB, etc. And then also having the Cortex-M processor providing deterministic real-time control of your, say, motor control system or other embedded system. So again, these are interesting devices which are allowing us to develop a new generation of application specific code that introduces a new era of embedded development. So this also gives us a number of different challenges. So we have to look at how we're going to partition tasks to run on these different devices, how we're going to share data between them, and how we're actually going to develop the code, and we need a new approach to our development tools as well. So today we're going to look at this third area, the actual code development, and how we can create applications to run on these two different processors on a single device. So typically on the Cortex-A we'll have a Linux operating system running. Then on the Cortex-M device we can run that with bare metal code or a small footprint operating system. And then those two processors have to communicate together through shared memory to build up the final application. So at the moment, ARM produced two different tool chains. There's the Keil-MDK, which is very much targeted at the Cortex-M processor. So this supports a very wide range of standard microcontrollers. It has its own development IDE called Microvision that again is very well targeted to developing small microcontrollers. So it doesn't really have any support for Cortex-A devices. Now there's another toolchain that's produced by ARM called the DS5 or Development Studio 5, and although this supports all of the ARM processors, it really is optimized to work with the Cortex-A devices to work with embedded Linux and particularly system-on-chip devices, and bringing up custom system-on-chip designs as well. Okay, so we have two tool chains which are perhaps at the moment not ideally developed to work with these heterogeneous devices. However, back in November, Keil and ARM released a new toolchain called DS-MDK, which is much more suited to working with heterogeneous devices. So now within the MDK range of products, there's the MDK Plus and MDK Pro. The DS-MDK license is now included as standard within those two software products. So if you buy or if you have the Keil-MDK Pro or Plus, you also have a license for this DS-MDK toolchain. So currently, DS-MDK allows you to develop for a range of application-specific devices. So these are the i.MX 6, i.MX 7 from NXP, and also their hybrid devices as well. And more recently, support's been added for the microchip SAM5 family. And again, other devices will be supported in the near future as well. So DS-MDK is an Eclipse-based toolchain that includes direct support for ARM devices and also direct debug support as well. Now, we've been experimenting with this toolchain, and our hardware platform that we've been using is a single board computer from a company called Phytec. So this is a small single board computer which is available with a module that supports the i.MX 6 or i.MX 7 processor. It provides all of the connectors so you can get it up and running very quickly. There's a breakout board that goes on the top that also provides a JTAG connection so we can do kernel development or debug the Cortex-M processor directly. And on the Cortex-A processor, it comes with a ready-made build of Linux. And there's also, very importantly, a Yocto build as well, so it's easy to customize the Linux installation as well. Again, these devices have support for cameras, so there's also computer vision development kits available for this board as well. So it's quite an interesting little development board, and it's available as a low-cost starter kit as well, directly from Phytec. So here, in our system that we've set up, we have an Ethernet connection onto the baseboard. We have the breakout board on the top, which provides a JTAG connection. And if you're currently using the Keil tools, you may have a Ulink Pro, which will also work as a JTAG debugger to talk to i.MX 6, i.MX 7, etc. So here we can control the Cortex-A processor and also the Cortex-M processor. So the DS-MDK allows you to develop applications using the GDB debug over Ethernet, and also we can control the Cortex-M processor via Ulink Pro. If you want to do Linux kernel or driver development, we can also use Linux Pro to develop those systems as well. If you have a more demanding application, ARM also produce a very high-end debugger called DStream. So as well as providing JTAG debug support, this also provides streaming trace to all of the various trace units that are within the Cortex-A processor and also Cortex-M. So again, this allows code coverage performance analysis and a high-level streaming trace performance. So again, with DS-MDK, we can make simultaneous debug connections to both the Cortex-A and Cortex-M processor. So both cores can be developed, both applications can be developed at the same time, and a full Cortex-A, Cortex-M application is easy to debug. So here within DS-MDK, we'll go on to look at it in more detail in a moment, but it allows you to develop both the A and the M support. The software interface, as we'll see in a moment, is also standardized between the A and the M devices, so it's very easy to set up communication between the Cortex-A and Cortex-M processor. And once we've built our application, we've got full multi-core support for all of the processors that are on the system. Now, if you've been using the Keil-MDK version 5, you'll be familiar with the pack system that's within the toolchain. Because there are so many devices that are that we need to support, it's impossible to install all of that support and can keep it upgraded with a single installation. So when Microvision 5 was introduced, Keil moved to providing a pack support system so that we can download a software pack via their cloud server and install it into the toolchain to support a given family. This is essentially a zip file which has all of the support files inside. This has now been added to the DS-MDK, and it allows us to provide software components and software support for these more advanced application-specific processors. So here, when we start DS-MDK, we have a view of the pack system, and we can select support for example, an i.MX 7, and download and install that into the toolchain. We can also download and install other support files, such as the Cortex microcontroller software interface standard files, the open AMP Asymmetric Multi Processing support, which we'll discuss in a little bit. And we can also install various different real-time operating systems, so the Keil-RTOS, FreeRTOS, etc. So this allows us to update and provide support for a wide range of processors very, very easily. Once we've installed that support, within the Eclipse environment, we can start a new project, and here we can start a project to build for the Cortex-M4 by selecting a CMSIS project. So this will be a project that's targeted at a Cortex processor. And then within the devices that are available, we can select the device that we want to work with. So in this case, again, the i.MX 7, and here we can select to work with the Cortex-M4. So this will set us up a basic project so that we can build a application to run on the Cortex-M4. Once we've started this project, we have the standard Eclipse environment, so we can add files and start to write code. But here we have an additional view called the Runtime Environment Manager that allows us to add components to our project to build up the platform for the code that we want to work with. So here we can, for example, add support for CMSIS core. We can add an operating system. If there's any board support or device support files, we can add those to control peripherals that are on the device. So this allows us to easily configure a project to run on the Cortex-M4, and then we can go in and start writing our application code. So it's making using the M4 very similar to how we would develop code on a small microcontroller. Similarly, if you're using the MDK, you'll be familiar with the templated and configuration wizards so that we can easily configure the operating system. And there are also a number of template files so we can easily build up a skeleton for the RTOS that we're using as well. When we create the project, a basic linker script file is added to the project so that we build the M4 code so that it executes in place. And depending on the processor we're using, a kind of a default script file is added. And this is available as a text file that's added to the project, which we can easily edit to tailor to our application. There's also a scatter file viewer so that we can look at this file graphically and it will show us the layout of our project. So as our code gets more complicated, we can see exactly how it's been laid out within the address space of the i.MX 7. Similarly, we can develop a project for Linux. So again, here we can just select a simple Hello World project. We can select the compiler that we want to use, so the GCC or the ARM compiler, and then we can build and run a simple Hello World project as a Linux application. In terms of debugging, we can use GDB, the GDB server, to download the Linux application, and we can then debug that within the DS5 debugger. At the same time, we can create a debug connection to the Cortex-M4 using the Ulink Pro, and then that will download and allow us to control the Cortex-M processor so that within the same debug view, the same debug session, we can execute the Cortex-M code. So this now allows us to build up two running applications, one within the Cortex-A and Linux, and the other running on the Cortex-M processor. So we can both run and control those within the single debugger. And the debug provides us comprehensive debug support. It provides us a low-level view of all of the peripherals that are within our application-specific device. So again, if you're doing driver development or you are developing code on the M4 and you want to see how it's interacting with the peripherals, this is very easy. It also provides us a wide range of RTOS support for a number of different small footprint operating systems. And if we're using the DS5 and to a certain extent the Ulink Pro, we can connect to many different ARM trace units that are available within the system. And setting up a hardware debug connection to these application-specific devices isn't actually a trivial matter. Within these devices, the core site debug architecture is much more complicated than on a microcontroller. There are multiple buses, multiple units inside, so it's almost a programming challenge in itself to get the best out of the debug system. So the DS5 has been set up with knowledge of the application-specific devices, i.MX, i.MX 7, SAM5, etc. So it will bring up those devices and connect you to each of the cores very quickly and easily. And that, as I say, isn't a trivial exercise. So now we have these two independent, freely running applications. So our next challenge is to connect them together so we can get some inter-processor communication and build up an effective application. So we need to synchronize our execution, and we also need to pass data between the two processors. So one challenge, if we could reinvent the wheel. So this would mean we'd need to write a Linux kernel module and write that to segment the memory, manage concurrency, and use shared memory to communicate with the Cortex-M processor. And then on the Cortex-M processor, again, we'd have to handle interrupts, manage the memory, and then try to connect the two together and get them working. So again, this is not a trivial challenge and could take significant time for us to develop. Fortunately, there is a standard way of doing this called Open AMP, or Asymmetric Multiprocessor Asymmetric Multiprocessor. So this is a standard interface that effectively does this for us. It supports heterogeneous multi-core processor systems. It allows the Cortex-A master processor to control the Cortex-M processor, and it provides a framework for managing the remote processor and a framework for passing messages between the two systems. So it really consists of two main components: remote proc, which allows the master processor to load code and data for the secondary processor, to control its reset. So once the code is loaded, we can start it running. It can also set up a number of communications channels that allows real-time communication between the two processors. And it also provides an API for the Cortex-M processor to initialize its communication channel as well. These communication channels are really using shared memory to communicate between the two processors. So using OpenAMP provides us a standard framework to join these two processors together. And this is OpenAMP is now, I think, part of the CMSIS standards, or has been incorporated into the CMSIS standards, and it's part of the software pack for the supported processors. So once you've installed the pack, adding it to your application is really a matter of selecting it within the runtime environment. So here we can tick a box, and then it's simply added to our project. So now it's built as part of the Linux operating system, and we also have the standard library that's been added to our Cortex-M application. So we now can communicate to the Cortex-M processor from Linux by a standard calls, making it look like a serial device. And then we have a standard API on the Cortex-M processor that allows us to send and receive messages to the Linux application. And so as a simple example here on the Linux application, we can instantiate the device. We can open it with a simple open command, set its attributes, and then we can read and write data to the Cortex-M4 processor. It really becomes as simple as that. And on the M4 side here, we're initializing the message channel, and then we're receiving data, and then allocating the transmit buffer, and then sending data out to the Cortex-A processor. So join the two processors together, we have a standard, easy-to-use framework that allows us this two-way communication. And the OpenAMP goes a little further in that it provides Virtuo access to the Linux drivers. So this is a form of virtualization that we can add a bridge and a Neo driver to the Linux application, so that we can now add a TCP/IP stack to the Cortex-M4 application, and rather than the M4 trying to talk to the Ethernet controller that's within the Cortex, the application-specific device, it can access the Linux driver through the bridge and send and receive TCP/IP packets through the Linux driver. So this is again a form of message channel that allows us to communicate down to resources that are within the Linux application. And again, this is pretty straightforward to set up. Within the runtime environment on the Cortex-M4, we can, at the bottom here, set up our networking stack as we would on a small microcontroller. We've added the OpenAMP support at the top, And then within the CMSIS driver section, so these are the low-level drivers which have a standard interface that would normally talk to the Ethernet MAC and PHY that's on the microcontroller. Here we have a CMSIS driver that talks through the OpenAMP messaging channel and into the Linux drivers themselves. So once we've configured this, we can start to use the TCP/IP stack the same way we would on a small microcontroller. So here we can call net initialize, the standard call to set up the stack, and then we can create a thread, and inside here we can create TCP and UDP sockets and send and receive data. So again, this is very much like using a small micro. Once we've built our application, at the moment the debugger is downloading the Cortex-M4 application into RAM, so it's hiding a bit of complexity for us. But to make a bootable system, we can effectively copy our M4 image into a directory that we can create in the Linux partition. We can then mount that directory so that it's connected to the boot sector partition of the Linux image. And then when we unmount, the M4 image will be stored in the boot sector. So effectively we've installed the M4 image into the boot sector of our application. And then with our bootloader, we can connect and boot that image at runtime. So we then load it out of the boot partition and install it ready to be executed in the RAM. Then when the Cortex-A processor boots, it can use the OpenAMP commands to start that processor running, and then we have a bootable system. So I hope that's been useful. If you need any further information, send me an email on the address below. It's also possible to evaluate DS-MDK or DS5, the full version, for 30 days. And in the UK, we have a limited number of the Phytec boards that are available for evaluation if you actually want to try this out for real. So I hope it's been useful for you today. And again, any questions, please let me know. Thank you very much.